Hey guys, Dr. Cadella here again. This experiment is the equilibrium experiment, and the equilibrium that we're going to be studying is that of phenolphthalein, which is a common acid-base indicator. Now phenolphthalein, when it's in acidic solution, is clear, but in basic solution it gives this vivid light red color. And we're going to see why. So this molecule is phenolphthalein in its acidic form. So when it's acidic, when the solution is acidic, it looks like this. This is the phenolphthalein molecule in its base form, the form that does have color. Now what happens, you guys, when you go from here to there, is you see this little proton right down here, this hydrogen. It's the one that gets pulled off in basic solution, and it looks like this in base form. Now, the reason that the base form of phenolphthalein, of the phenolphthalein molecule has the color that it does, has to do with what's called conjugation. And what that means is conjugation is the reason for the color. And what we're talking about there is this. If you look at all of these carbons, there's alternating double and single bonds. Now, if you remember back to Chem 101, go back to hybridization theory, we know that these carbons have 3 electron groups each on them, and that means that each of these carbons is sp2 hybridized. And what that means is that the electron group geometry about that carbon is trigonal planar, so it's flat. But there's that one unhybridized p orbital that's perpendicular to the plane of the molecule. It's sticking up and down. It's a p orbital, and that's where these pi electrons reside. Now, if you look at this, there's sp2 carbons all the way around here, sure, but there's also one here, here, connected to here, and we have alternating single and double bonds all the way through that molecule. That's what we mean by conjugation, okay? And the reason that's relevant and important is that every single one of those carbons that's connected like that is sp2 hybridized. And that those sp2 hybridized carbons each have an unhybridized p orbital sticking up. And they overlap. And so that means, guys, all of these pi electrons are delocalized throughout the whole molecule. So they're not just stuck right there. These 2 electrons are spread out over the entire molecule. And what that does is that lowers the energy of the electrons in the p orbitals enough so that they can absorb and emit visible light. Whereas, if we go back over here, this carbon in the middle is breaking up that conjugation. It's sp3 hybridized. There's 4 electron groups on it, no unhybridized p orbital. Those electrons now, pi electrons, are stuck in the different regions of the molecule. Less conjugation, higher energy electrons, does not absorb visible light, does not emit visible light. So that's why that has that color over there. All right, so let's get to the experiment. So our goal is to determine the equilibrium constant for this molecule. And because this is an acid-base reaction, it's donating a proton, it's the Ka. The equilibrium constant is the Ka. Now, for this reaction here, the Ka looks like this. Concentration of the hydrogen ion, concentration of the base form. This ion minus, it means the base form. HIN means the acid form over here. So the concentration of protons times the base form over the acid form. So we need to get, basically, one way to get it is to get these 3 values, these 3 concentrations, and I'll tell you how we're going to get that. Another way that we're going to do that is if we plot the pH, which we can measure, versus the log of the base form, the concentration of the base form over the concentration of the acid form. This is the Henderson-Hasselbalch equation. It tells us that there's going to be a linear relationship where the y-intercept of the best fit straight line is the pKa. Now, you know, if we know the pKa, the Ka is just 10 to the minus pKa. So that's a second way where we are going to determine the equilibrium constant, the Ka, for this reaction. So, coming back over here, the way we're going to find the concentrations of the proton, the base form, and the acid form of phenolphthalein is with a spectrometer, colorimeter. Now, this is called Vere's law right here, and this says that the absorbance of a solution is equal to epsilon B times the concentration. This epsilon B, this is called the molar absorptivity, and this is a path length. We don't care. I'll tell you why in just a minute. Okay? Basically, it's just some number which we're going to find. So what this says is that if we know the absorbance, we measure the absorbance, we know the concentration. Now, what gives it the concentration? What gives the concentration, the color rather, is the base form. And so what we're going to measure with the spectrometer is the concentration of the base form by measuring the absorbance. So, and this is how we get it. Just rearrange this guy a little bit. We can, if we know the absorbance and epsilon B, we know the concentration. So, how do we get epsilon B? Easy. This is what we call solution F in the procedure, buffer solution F. So Matt made up these different buffer solutions that have different pH buffers. Remember, a buffer fixes the pH of that solution within its capacity. So whatever it's buffered at, that's the pH of the solution. And Matt made solution F such a high pH, so basic, that we can assume that all of the acid form has been converted to the base form. And so we'll know the concentration of the acid form. That's going to be our initial concentration. And only for solution F, guys, is that equal to the concentration of the base form. But you see, what's nice is that gives us our C in Vere's law. We'll measure the absorbance, and we can find epsilon B. The product of the two is just a number. Now we have it. We can use it for our other calculations up here. Now, one other number that you're going to need is the concentration of the phenolphthalein, the initial concentration that we're going to use. And that's right up there, 0.000207 molar. 2.07 times 10 to the minus 4th molar. We see that we basically need to know hydrogen ion concentration. Well, that's easy. We have a pH probe. We can basically just put a probe into the solution. That gives us the pH, and we know that the concentration of hydrogen ion is 10 to the minus pH. Easy. We've got that. And in the calculation section, I talk about how we're going to get the other two concentrations. But it ends up, what we need is we need to know C, the concentration of the base form of phenolphthalein at that pH. So what we're going to do is we're going to make up solutions A, B, C, D, E, and F, and a blank. We're going to measure the pH of A, B, C, D, E, and F, A, B, C, D, and E, rather. And we're going to measure the absorbance of A, B, C, D, E, and F. Knowing the absorbance, we can get the concentration. pH gives us a hydrogen ion concentration. So let's go do that. All right, guys, so now for the experimental part. All we have to do really is make up our solutions, measure the absorbance of our solutions, A through F, and then measure the pH of solutions A through E. Before we can do that, though, before we can measure the absorbance, we need to make up a blank so that we can calibrate the colorimeter. Now, colorimeter, we want to be at 565 nanometers this time, so we're going to make sure that that green light is on the 565. And to calibrate it, we're going to take our blank solution. Okay, we still have to make that. The blank solution has 18 milliliters of buffer solution A in it, and I'm going to add 2 milliliters of ethanol. I put that in. Notice it has no color. Take the blank, pour it into our cuvette. Up to the opaque portion. Clean off the cuvette. Pop the lid on. Place it into the colorimeter, the spectrometer. Close the lid. Press the cal button. Just like with the kinetics experiment, once that red light stops flashing, it's calibrated, and we're finished calibrating it for the entire experiment. All right, it's calibrated. Now, to make up our other solutions, A through F, I've already made up B through F. I just want to show you how I do it with solution A. So each of these solutions, guys, has 2 milliliters of phenolphthalein in it. Now, the concentration, the 0.00027 molar that you saw a little bit ago, that's the concentration in this bottle right here. Now, in each of these solutions, it's going to be diluted 2 to 20 or 1 to 10, which means when you calculate the concentration of the phenolphthalein that you add, the initial concentration, you have to use the dilution equation to calculate it in here. You only have to do it one time because it's the same for all of those. So what we do is I'm going to add 2 milliliters of phenolphthalein. I'm going to make up solution A. And I measured this out with a graduated cylinder, so it's 2.0 milliliters. And then 18 milliliters of the buffer solution. This is buffer solution A. So it's 18.0. I add that. And now I have my color. Remember, the color comes from the base form of the phenolphthalein molecule, and the higher the pH, or the more basic the solution, the more molecules of phenolphthalein there are that are in the base form, and the deeper the color. So it looks like this. You can see it goes from light to dark, because solutions A through F go from lower pH to higher pH, less basic to more basic. All right, so we have our solutions all made up. All right, so now we're ready to measure the absorbance of our solutions. So we'll take our blank, pour it out. Now, we have to be careful. We don't want to change the concentration of any of these that we made by diluting them with what was there before. So all we do, okay, so now there's still some of the blank in here, and that would dilute this. What I do is I take a little bit of buffer solution A, not a lot, just a little, pour it in there, put the cap on, and shake it up. Pour it out. Now, even though there are still droplets in there, that's droplets of beaker A. So it's not going to change the concentration when I add more A. So it's good to go. So I add beaker A, bring it up to the mark there, and about right there. Put the cap on, clean off the sides, pop it into the calorimeter that we just calibrated, close the lid, and read the absorbance from the LabQuest. That's it. We're done with that. Basically what you do now is you do the same thing for B, C, D, E, and F, and we're finished measuring the absorbance. All we have left to do is measure the pH. To do that, I have 5 test tubes here labeled A, B, C, D, and E. So I'm going to take buffer solution A, pour it into test tube A. And likewise, B, C, D, and E. Remember, we don't have to measure the pH of buffer solution F, because the only purpose of buffer solution F was to get our epsilon B for Beer's law. And we got that from the absorbance, so we don't need it anymore. So to measure the pH, use a pH probe that we attach to the LabQuest. So now we're measuring pH. Now, the pH probe comes in a storage solution. We need to take it out. We need to rinse off the pH probe. pH probe, by the way, okay, it's kind of cool. It has a little glass bulb in there, and inside of there are basically a couple of wires. And what this does is it measures the conductivity between those two wires inside of the glass bulb. And so when you put this into a solution, the concentration of the hydrogen ion affects the conductivity because it migrates through the glass and into the solution. Now that's important because it doesn't happen instantaneously. It takes a little while. We have to let it sit in the solution for a few minutes so that the hydrogen ions can migrate and give us the pH. First, we need to clean it off, right? So, rinse off the probe, pat it dry gently with a Kim wipe, and ready to go. So I'm going to take this, pop it into solution A, give it a minute to equilibrate, read the pH from the LabQuest. and it's still changing, so I have to wait a few minutes. Once this finishes, we're going to do the same for B, C, D, and E, cleaning off the probe between each measurement, and we're done. That's all there is to it.